So for the cross-section view, this is Y, and this is our Z. Okay, then right-hand rule, this is rotation about dx. Okay, so so on the left-hand side, we have our cross-sectional view. On the right-hand side is the structure. Okay, so we can see the structure is more like simply supported. So we know, okay, the normal stress allowable. So we see what is given to us. Okay, so the normal stress allowable is equal to 8 KSI. So some of you might ask, Eugene, what the, why are we given normal stress? Okay, so later on I'll explain. So then the next one is the shear stress allowable. Okay, so this is equal to 3 times 10 to the power 3 KSI. Oh no, 10 to the power K PSI. Eugene, wake up. Okay, times 10 to the power 3 PSI. Okay, this is also PSI. So these two are not for the joints, are for the wooden structure. Okay, these are for the wooden structure. And then the next one is where the joint. Okay, so we are given the spacing. Which is S is equal to 6 inches. Right? And next we are given the F, the force, okay, is equal to 600 pounds. Okay, so this is the fastener resistant force of fastener can resist, right? The fastener can resist under single shear configuration. Okay, under single. So now if we look into our fastener now, okay, so we realize that the fastener is under. Can anyone tell me if you look at one fastener down here, okay, is it single shear or under double shear configuration? Anyone, please? Anyone? Can you remember?
Would that be single shear?
Good guess. No, it's double shear because you have left and you have right. Let me elaborate. Okay, let me elaborate. I think you guys, Dr. Koshi taught you single shear and double shear configuration. Yes or no?
Yeah, we just
Right?
haven't seen one exactly like this, I don't think.
Yeah, I know. I totally understand. Okay, so I'm going to draw this. Okay, so if I'm going to draw based on your textbook. By the way, if you feel that I'm moving the right patch too quickly, tell me. Okay, I will go back and you can copy. Okay, so let's look at single shear configuration. Okay, let's look at single shear configuration. So if we look at a single shear configuration, you have this. Okay, you have this. So you have right. So you have your bolt going through, or your nut, whatever it is. Okay. Then you have a coupled force. So you have P. The other side is your P prime. Okay. So this is what we call single shear configuration. So shear stress is equal to P divided by area. Okay. So the area that we are referring to is the what? Is the cross-sectional area at this part. Okay, so this is where our area is. Yes or no? Right? So that's why the area is equal to pi r squared. Okay, so now if we look at the double shear configuration, okay, now we go into double shear configuration. Okay, so what we have is now like this. So now it looks like this. You have one piece of wood over here, this, and come down, right? Then you have sorry. Then you have a bolt going through. All right, so this is our bolt and nut, whatever it is. So now you have cross section. Can someone tell me what's the formula, please? Anyone? So this
C divided by 2a.
Yeah, well done. Why 2a?
Because there's two areas
Well
in
done.
that configuration.
Well done. Okay. So you have your shear stress. It's going to P divided by twice the area. So the area that we look at is here and here. Okay, right? So it has to like shear twice the area. Okay. So if you look at this, right, the single shear has higher stress. Let's say P is a constant, right? Let's look at the equation. So let's say P is a constant, area are the constant. Which one will generate higher stress, single or double shear? Hello. The single shear, yes or no? Right? Okay, so single shear, I'll write down here note single shear will generate higher stresses, higher shear stress. Okay, right. So now we know. So let's look at this structure now. Okay, so I'll leave it a bit for you to write. Now we will take a 5 minute. Y'all want a break or we just carry on until 4:10? Hello. Okay, you all let me know later. Okay. So now let's look at the failure mode. Okay, so there are three. Okay, so there are three. Okay, there are three. Okay, there are three possible failure modes. Okay, so you see now, right? Now we are going to failure mode analysis already. Okay, this is what engineers are supposed to do, right? Only if you know how the structure will fail, then you know what to calculate. Okay, if you don't know how the structure will fail, you calculate everything. Okay, and I'm not saying that we can't do that. We can absolutely do that. Okay, but we don't want to do that. Okay, I want you to make you to become intelligent engineer. The real intelligent engineer, not artificial intelligent engineers. Okay, real one. Okay. So anyone, what's the mode one of failure, please? Anyone? I'll give you the first start. Okay, so it's the shear failure. Okay, of the fastener. right? So we are given the property of single shear. Right, single shear force for a fastener will be equal to 600 pounds. Right, and another thing that we are given is the spacing that we have decided to use is S equal to 6 inches. Now, in real life, okay, in reality, let's say we start this one clean sheet, okay? You're going to build a structure, something like that, okay? You decide the spacing. I repeat again, you are the one that's going to decide the spacing based on the loading condition. Okay, no one is going to decide on the spacing except what? You, okay? Then the next thing, how is the structure going to fail besides if the nail don't pull out? What's the next thing? Anyone?
Is it shear failure of this wooden structure?
Well done. So the next mode of failure, well done, okay, is the shear failure of the wooden structure. Okay, well done, of the wooden structure. So now, if we were to look at here, this is the wooden structure. Can anyone tell me where is it going to fail? Anyone? So if you look at a cross-section view now, where you can see the 6 inch, 0.5, 0.5 inch, 2 inch, 2 inch, right? You can see those geometry. Where is it going to fail? Anyone, please?
At the joint?
No, we done once already. At the joint is mode 1. Mode 2 of failure is where? So one mode of failure is at the what? At the joints. Okay, so this is mode number 1. Mode number 2 is going to be where? Anyone?
In between A and B, it's going to bend until it breaks.
No. We are looking at the cross-section view now. This view.
Oh.
Is it where
So where's
it's like at the
where?
plywood?
Huh?
At the plywood where it's just the plywood?
Well done. Why?
Because that's where T is the smallest and Q is the highest.
Hallelujah. Okay, I like that. Okay, that is where. So it's going to fail at the where? Centroid. The location of centroid, because the thickness are so what? Small. See, you guys are unconsciously doing failure analysis based on the formula already. Wow. So shear failure of the wooden structure, and we know the shear stress allowable is equal to what? Is equal to 3 times 10 to the power 3, right? PSI, right? 10 to the PSI. Then after that, we know that this will be equal to VQ over what? IT, right? And the third mode of failure is where? Is what? Anyone? So the third mode is like what it said before, normal stress failure. Okay, normal stress failure of the wood due to bending moment. Okay, due to bending moment. So the formula what we are given is shear normal stress allowable is equal to 8 times 10 to the power 3 psi, and the formula we are going to use is equal to my over I. Right? My over I. Now, question for you. Due to bending moment, where is it going to fail? Based on the cross-sectional view. Hello?
Would it be the thin plywood at the either at the outside?
So is when you say outside is the extreme top or bottom, am I right?
No, I mean like along the centroid, as far out from the center as possible. That's where
Yeah.
it's going to crack.
You are absolutely. So the failure can be either at the top, at the bottom, due to normal. Yes or no?